Okay, everyone. Today we have some exercises that take the whole idea of a linear function, y equals mx plus b, a linear equation, and takes it a little farther and tries to apply it to comparing some rates and such. So let's take a look at number one here. It says Brad rakes a field. I guess I should say Brad rakes a field or his field. Brad rakes a field at a constant rate of 4 square feet per minute. All right, now as soon as you see that constant rate, that tells you that you have a linear equation, a linear situation here. So that means that you can describe this with an equation that looks like y equals mx plus b. All right, so it says assume that he rakes an area y in square feet in x minutes. All right, and we want to express the situation as a linear equation in two variables. So, like we were saying before, what we should be looking for, I'm going to turn on my blue here if you give me a minute. What we should be looking for is something that looks the form y equals mx. Whoa, hello. Y equals mx plus b. All right, so I'm just going to finish putting that down here. All right, and I think I want to change that blue just a little darker. There we go. Okay, so he wants, or we want an equation that looks in the form y equals mx plus b. All right, so they tell us that we're going to use the variables y and x, so they can stand right there. They can stay where they are. And the slope, well, the slope is just going to be equal to the constant rate at which he works. So that 4, they tell me that's a constant rate of 4. So I'm going to plug in that 4 right into, I'm going to plug in that 4 right into where we have our m. All right, now what would be my y-intercept? Well, these two variables, they're describing how much work he gets done, how many square feet he gets done in X minutes. Well, if you think about it, if he works 0 minutes, then he would have 0 work done. All right, so that's one of the points that works for this equation is the point 0, 0. All right, so if I were to plug a 0 in for y and x, well, if I do that right here, well, this part is just going to be 0. And so I can drop that out. So that really means that b is equal to 0. Okay, so what I'm getting to is my equation then can just be simply y equals 4x plus 0. But I don't really need to write that plus 0 there. So there's my equation of this line. All right. Now they ask me to graph it, and I'm going to leave this part here. I'm going to turn on my graph here, and that's going to cover up some of those words. That's okay. That's okay. We're done with those. So they want me to graph this situation here, this line. All right, notice we only gave you the first quadrant because it wouldn't make any sense for him to be raking in a negative amount of minutes. All right, so this is going to be x down here, and this is going to be the minutes, right, that he rakes. I'm going to redraw that, make that look a little better. Minutes that he rakes. And then y is going to be over here. That is the area that he has raked. All right, so let's graph some points. There's many ways to do this. We could make a little chart. We could make a little XY chart like we've done for a while now. We could pick some X's and plug it in and get some Y's. Or we could just simply use the slope and the y-intercept. Well, the y-intercept here is 0, so that's that point right there. The slope is 4, so I can simply go up 4, 1, 2, 3, 4 over 1. And there's another point that works. Up 4 over 1. Okay, up 4 over 1. So that would be a graph of this line that would describe his work that he's getting done. Now this graph only would show you over the first 4 minutes. All right. Now I probably want to know what he's going to be doing farther than 4 minutes into his job. Okay. So let's do this. Let's change our graph. I'm going to take this off of here, and I'm going to make this a little more spread out. How about we get a little farther out with our minutes here? How about we make each one of these blocks a quarter of a minute? All right, how many would that get us? We could have 1, 2, 3, 4. That might not be that many. Let's go each one of these blocks is a half minute. All right, so that means I'm going to have 1 minute here, and that's going to be 2, 3, 4, 5, 6. Okay, just so I get some more minutes in here, because with a slope of 4, that's going to go up rather quickly. All right, so I'm going to map it out like that. That's going to be my minutes. Okay, and then since I do have this slope of 4, since I'm going up 4 every time, why don't I go? Let's try this. Let's go. Every other block is going to be 4, so that's going to be 8. That's going to be 12. That's going to be 16. That's going to be 20. That's going to be 24. Okay, so now let's try this graph again and see what happens. 0, 0 is still going to be the same. And we're going to graph 4. We're going to have a slope of 4, so we're going to go up 4 over 1. Okay, up 4 more over 1 more. Up 4 more over 1 more. And you see, this is making a little better graph. I'm going to be able to get some more information off of this graph. And there we go. And now I can try to draw this line again as straight as I can. Oh, that's really bad. I'm going to redo that one right there. Okay, so we're going to try to draw this line. Still not the best line in the world, but wish I had a ruler I could put right on here. Okay. All right, so that's what my graph is going to look like. Now what I can do is I can use this graph, right? I can use this graph. Let's turn that off. And let's turn this other part on. It says, use the graph or the equation to determine the total area he rakes after 12 minutes, 1.5 hours, and 3 hours. Okay? So now our graph, even though we made it much bigger, we made it go out to 10 minutes here, we still really couldn't get this off of the graph what he would rake in 12 minutes, 1.5 hours, or 3 hours, because it just simply doesn't go that big. All right. If we wanted to do that, we'd have to get at least out to 12 minutes here to see what our graph would be, and we'd have to change the scale again. All right. So let's just use the equation. The equation is y equals 4x. Well, what they're giving me is the minutes, so that is my x value. All right. So what if I plug in a 12 into this equation? Well, I'd get a y value of 48. All right, so he could rake 48 square units. All right, whatever that units was, I forget what it was. Whatever units they're using of yard in 12 minutes. So I could put that right here under my column chart here. All right. Now, they also asked me 1.5 hours. Now, be careful. I can't just do this. Don't do this. Don't go 4 times 1.5, because that is in hours, right? And our x is supposed to be in minutes. All right. So we have to convert that 1.5 hours. Well, that would be 1 hour would be 60 minutes. All right. I'll put that up here, 60 minutes. And then another half hour would be 30 more minutes. So I'm looking at 90 minutes total. So I'd put a 90 into there, and that'd be 360. So if he raked for 1.5 hours, which is 90 minutes, he's going to rake 360 square units. All right, and 3 hours, I want to do the same thing. 3 hours would be 180 minutes. All right, and if I multiply those, I'm going to get 720. All right, so 180 minutes is going to give me 720 square units that he is going to be raking. All right. So, like I said, big finish to kind of this note packet that we're getting towards the end here. Um, we're trying to take now this y equals mx plus b and these linear equations and use them in word problems. All right, so let me clear the deck here. Let me get this off here, and we'll go into exercise number 2. All right, here is exercise 2. Now this one is a little different. It's similar, but we're starting you with some different information here. Instead of giving you the constant rate at which someone is raking or running or whatever, we're giving you a graph. All right, and from that graph, you can see that this is definitely a straight line. So it is definitely a linear function or a linear equation. All right. And this graph gets much bigger. This graph goes up to over 180 minutes, and we're talking about distance. And this is describing how fast or the distance that Josie ran on a recent race. Okay, so one of the first things they ask us is use the graph below to determine Josie's constant rate. And again, that is important. If they didn't tell us it was a constant rate, we couldn't say it was a linear equation. All right, but they do. So that means whatever equation describes this motion, it's going to follow y equals mx plus b. All right? So, first they want us just to find her constant rate of running. Well, rate in this case, rate is going to be the same thing as slope. And it did it again. I gotta get that out of there. All right, I gotta watch that. Okay, so rate is going to be the same thing as slope. Let me finish my wording there. There we go. Okay, so if I can figure out my slope off this graph, then I can figure out her rate at which she ran. All right. Now let's take some real easy points here. Let's take this point right here. Well, that's 0, 0. Okay. Why not use it if it's there? Now what we have to do is we have to find a point, and we've done this before. We have to find a point that crosses these grid lines, all right on where these grid lines come together, all right? We want to use a good point to figure out her rate of running, all right? Now, and part of this is you want to pick points that are far apart, okay? The farther apart, the more accurate your rate is that you're going to get here. All right, so I'm going to use 0, 0 because I know that one is definitely, if she runs at 0 minutes, then she's going to go 0 miles. All right, so I know that one is spot on. All right, so I'm going to go over here. I'm going to pick this point right here. Okay, and if you look really close at this point, it's not directly on where two of these cross. It is right on this point right here, this coordinate right here, and it looks like they're going by tens. All right, so that is definitely 170. Okay, so part of my coordinates, I'm going to use 0, 0, and the other coordinate I'm going to use is 170. And I want to go up here and figure out, well, what would be the distance? And if it was right on this line, it would be 12. Okay, but it looks like it's right below that line. So I want to estimate here, and I want to say I'm going to estimate that to be about 11 point. I'm going to go with 11.8. All right, so 11.8 is going to be my y value. All right, so I'm going to figure out the slope. All right, and we know slope is equal to m, but I'm just going to write it as slope this time. And what I do is I take my second value of y, and I subtract my first value of y. So I'm looking at these two right here. That's what I'm subtracting right now. There's my y value. So I'm going to put that over my first value, or my second value of x, and take away my first value of x. And look at how easy is that if I use 0, 0. All right, that's the nice thing about some of these that go right through 0, 0. It's very easy math to do that. All right. Now, usually what we've done is we have left slope as a fraction. Okay, but in this case, it really doesn't. We don't need to. All right, we don't need to leave it as a fraction. I'm going to bring up my calculator here, and I'm going to take 11.8, sorry, and I'm going to divide by 170. 70. All right, and that I get 0.069. I'm going to round that to 0.07, and that's going to be miles per minute. All right, so there is Josie's rate of running. Okay, and I got that all off the graph. Now, depending on what point you pick over here, you may get a little different number here, but it should be very, very close. Even if I use 12 here, if I would use 12, then that would be okay. I mean, that's pretty darn close to 12, but we want to be as accurate as possible. If I use 12, I would have got a very, very close number here. So that's what I'm determining her rate to be off of the graph. All right. Now the next part. Well, we already did that part. Her constant rate is equal to the slope. All right, so we already did that part, so I can turn that off. The next part says, Rebecca just finished a marathon where she ran 5 miles in 1.2 hours. So I'm going to do the same thing. I'm going to figure out her constant rate. All right, so I'm going to put 5 miles. All right, and I've got to move this down a little bit so I can actually write the whole number here. 5 miles over 1.2 hours. Okay, now you got to be careful here because look at, we've got miles per minute over here, but they're in miles per hour. Okay, so first thing I'm going to do, I'm going to change that to miles per minute. Okay, and if I go to my calculator, if it's 1.2 hours, 1.2 hours, okay, and I multiply that by, well, I've got 60 minutes in an hour, that's 72 minutes. Okay, so I'm going to get rid of that. I'm going to put down 72 minutes. Okay, so she ran 5 miles in 72 minutes. Now, I'm going to do the same thing I did up here. I'm going to take this slope. This would be the slope if we made a line with how fast Rebecca ran. This would be the slope of that line, just like this up here was the slope of this line. All right, so I'm going to do the same thing. I'm going to divide the two. I'm going to take 5, and I'm going to divide by 72. And I get 0.069 again. Look at that. I get 0.07 again. All right. And so if I round to the hundredth, they actually ran at the same rate. All right. If I were to redivide that, let's see, what did I get before? I got 0.0694. All right. Let me write that one down. 0.0694. Okay. And what did I get for this other one? I got 11.8 divided by 170. That was 0.0694. Look at that. Look at how close that is. All right. And I honestly don't think we should go any further. I wouldn't go out any further than that. I mean, how do you go to tens, hundreds, thousands, 10,000ths of a second here? Okay. So, boy, they actually ran at the same rate. All right. So that's going to happen. Alrighty, so let me turn this off. That's exercise 2. I think that's all they ask us to do that. Yep, that's exercise 2. So I'm going to turn this one off, and we'll go on exercise 3. Okay, here's exercise 3, and this is just another different way, really, of asking you the same thing. It says Joe can read 6 pages of text in 10 minutes. All right, so right away I'm thinking, that I'm going to turn that into a rate. It even says, assuming he reads at a constant rate, write the linear equation that describes the situation. Well, his rate, again, would be equal to his slope. All right, so those are the same things. So I'm going to take 6 pages, write down 6 pages, over 10 minutes. All right, because whenever you make a rate, you put the time on the bottom. All right, and I'm going to leave that as 6 over 10 because I hate to round in the middle of a problem here, and that will reduce to 3 over 5. So his rate is 3 pages per 5 minutes, and that's going to be his slope. Now, this is similar to a previous one where if we want to plug this into y equals mx plus b, well, so far I have 3/5. And what is that b going to be? Well, if you think about this problem, if he reads 0 pages, well, that's going to take him 0 minutes. All right, so that is a point that works for this equation. All right, and that means if I plug 0, 0 in for y and x, I'm just going to get b equal to 0. All right, so that means my equation is going to look like that. There's my equation. All right. Now, they also say that the following table represents the number of pages that Bob can read. All right. Now, this is Bob, and of course, this is Joe. All right. So we want to see which one of them has the faster rate. Okay. Well, similar, this could be like points on a graph, 4 comma 3 and 12 comma 9. And let's see, 14 comma 13 and 20 comma 15. Those could all be points on a graph that would describe how fast Bob can read, or how many pages he can read given number of minutes. All right, so again, we want to figure out Bob's slope given this information. So really, you just take 2 points. Let's take the farthest two. Let's take this one, and let's take this one, and let's figure out his slope, or his rate at which he can read. So I'm going to take change in y over change in x. So my change in y is going to be 15 minus 3. And my change in x is going to be 20 minus 4. So what am I going to get here? I'm going to get 12 on top, and I'm going to get 16 on the bottom. And if I reduce that, all right, again, I'm going to try to stay away from some rounding. So I'm going to reduce that. 12 over 16, they're going to both divide by 4. And I'm going to get 3 over 4. All right, so that is his rate. Okay. Now, if I were to make this into a linear equation, it would just simply look like this, just like the one up top, but a different slope. All right. Now, which one of those is faster? He can read, if you put the units back in, that means Joe, switch to red here, Joe can read 3 pages, okay, in 5 minutes. Okay, and Bob, put Bob in this lovely color, Bob can read 3 pages in 4 minutes. Now, if you have to, you could divide those two and see which decimal is greater, but I think it's pretty obvious if you look at this. He can read 3 pages in 5 minutes. Well, he can read 3 pages in just 4 minutes. So obviously, that is moving faster. So Bob reads at the faster rate. Okay, so there's another application of where you can use your rate or your constant rate, similar to a slope, and then you can see which one's going faster, which one's going slower, etc. Okay? All right, so hopefully those went well. Hopefully you don't have to rewatch them, but if you do, that's great, because then you can listen to my lovely voice again, so that would be awesome. And have a good night. Thanks for listening. We'll see you tomorrow.